one more random mastery test practice, and then we'll get on to our other things. So find the derivative with respect to x of this function. So find g prime of x. So when you're looking at something like this, make sure you're thinking about overall structure or last operation in terms of order of operations. What connects all of this together? In this case, it should be definitely a quotient. So make sure you know quotient rule. But quotient rule requires knowing how to find the derivatives of each of the halves of the quotient, which each of those is a little bit of a mess. Although these aren't individually the messiest expressions maybe you've seen, like it's not 3 levels of chain rule or a lot of arc trig something or another functions. It's still not too simple. So quotient rule, we need to find the derivative of the top and the bottom pieces of this fraction, both halves of the quotient, but remember not to just stick them back together. Remember to put them together with quotient rule, which is kind of like product rule with a subtraction and a denominator. So logarithms are the 1 over sort of function derivatives in general. This is log base 2, and it's not just of x, it's of 4x, so there's going to be a little bit of chain rule, not too much. And a natural log of 2 that shows up when we work on the derivative of that numerator. Now in the denominator, we've got an exponential function. It's not just 3 to the x, but it's kind of close. So the derivative of that 3 to the square root of x is going to contain as a factor the whole original function, 3 to the square root of x, and then a little bit of chain rule times the derivative of that exponent, the thing that was actually done to x first, which is its square root was taken. And then a cosecant function subtracted, but subtraction is an easy part. Cosecant's derivative, a little bit messy, but subtracting the derivative of cosecant of x is subtracting a product of a couple of trig functions, also just of x, so no chain rule on that part. So altogether, the derivative of the numerator, without simplifying, so don't go through and try to simplify stuff on your mastery test. Maybe put the 4 on the top instead of off to the side, but it would look something like this. Obviously, in reality, it would cancel with the factor of 4 in the denominator, but I'm not going to be all fancy and try to reduce things here. The derivative of the 3 to the root x part, I would have 3 to the root x and times 1 over 2 root x, or 1/2 x to the negative half, however you want to think of square root of x's derivative. And you can do either one of those. Also, this natural log of 3. Log base 2 gets a natural log of 2 in its derivative. It's in the denominator. 3 to a power gets a natural log of 3 in its derivative. And this cosecant of x, cotangent of x, it was subtracting the derivative of cosecant of x. The derivative on its own has a negative in the front, so when we're subtracting that negative expression, that's where the plus comes from here. But the derivative of cosecant of x is cosecant of x, cotangent of x with a negative, so minus the negative gives us a plus. So putting this all together is a mess. But if you think about the individual parts, break it down into smaller components and work on those individually so that you don't make mistakes. Thinking about things you can do on your mastery test, on longer problems, you'll have a significant amount of space around them to show your work. You could set up something like this where you write out all the derivatives separately, but do make sure you put them all together in the end. Don't just like draw arrows and say put this here. Do please write it out as a full final expression. This one's rather long, but this is just putting the pieces together. So like maybe write out even quotient rules so you don't get tangled up while you're thinking about or focusing on all the other things. But okay, I need a prime of x and b of x, or whatever you want to call them, f's and g's. Put those into their positions, and then minus the original a of x times the derivative of b of x, and then divided by the original denominator squared. So make sure you remember parentheses around the denominator when you square it, unless it was just a number, in which case you wouldn't really have needed to use quotient rule, or just a single x. You do need parentheses around it to get the whole thing squared, and please don't square things out, like don't distribute or simplify, just do the calculus and then stop. Please don't do excessive algebra. Like I said, if you put this 4 on the top of the fraction instead of off to the side, that's simple enough, like I can see what you did, but don't start reducing, simplifying, expanding, combining like terms and that sort of things. Just as opposed to usually in math classes, just leave it in a messy form, but it actually makes it easier to see that you have all the parts. If you have, oh, this part's the derivative of a, and this part's the original b, and all the pieces are just there and easy to see. That way, if all you did is skip a negative sign, but you'd gone through and combined all the like terms, I can see that it was just a negative sign. So on the longer problems, like something like this, they're worth 5 points on the mastery test, and you can get partial credit. It's not just all or none 5 points. The short questions, you just either get them or don't. The first page of said 25 questions, it's just something like one of the pieces of these, like log base 2 of x, or 3 to the x. Those you either got it or you didn't, all or none. But longer questions like this are worth 5 points, and you can get anywhere from 0 up to 5 points. Whole number increments, but you can get partial credit on those. So if you make a small mistake and it's, you can figure out what you did, then just a point off. So study well for the mastery test. Again, it's tomorrow night, 4 to 7. It's not a 3-hour-long test. It's a window because I know this is not a regular class time, so just come when you can, leave when you're done. I anticipate it'll take you between 30 and 45 minutes to finish this, but however long you want to stay, you're welcome to work on it. The room number, it's in EDC. The room number is in the announcements. If I say it, I'm sure I'll get it wrong, like switch around numbers or something. So just read it in the announcements in Canvas. But 4 to 7 p.m., I'll be there a little bit early. It's going to be don't go in and find your favorite seat before I get there if you beat me there, because I'm going to have everybody leave the room and come in, check in, and get a test for me, and then you'll be assigned a place to sit. So just bring your ID, bring something to write with. Pen or pencil, I don't care, but if you are planning on making mistakes, don't plan on making them, but but yeah, bring something that you might be able to erase with. That might be better. You're welcome to write in whatever you want, though. Not highlighter, I guess. But in any case, that's tomorrow night. So I will be there the whole time. And Axel is going to be there, and Julia, one of the TAs from the other section, is also going to be there, not to help you do the test, but to make sure that you can get in and out quickly when you're ready to go, and to make sure that everything's quiet in there so that you can concentrate. So please, when you come, don't bring a lot of stuff if you can avoid it. Like, don't bring a snack. There's no eating during that test, so just bring yourself, bring something to write with and an ID, and as few other things as possible, because you know how it gets cramped in tests and people need to get in and out. The less difficult it is to get in and out, the easier it will be to concentrate. All right, so that's tomorrow. Today, what I want to talk about is there's on your next regular tests, like a Scantron test that's not just did you memorize these rules properly. It's in just a couple of weeks. It's between Veterans Day and Thanksgiving, that week in between there. It isn't a test of just do derivatives because we did that already. So it's going to cover the other things we talked about before we started memorizing all our derivative rules, just like what do they mean? How do we construct them? How the process of getting from an exact accumulation to an exact rate of change function and how that works, as well as the meaning of rates of change, which some of that we talked about as we were starting from rates of change. Obviously, we're going kind of back and forth in two directions. Before your last test, we focused on how to get from an exact rate of change to an exact accumulation, but we stopped just before we got to the integral part. There's going to be a bit of working with integrals or writing integral expressions to represent exact accumulation, so that's part of it. But also, since now we know how to find rate of change functions in their closed form, we can also look at a rate of change function and know what it must have come from and write accumulation functions. They're exactly in a closed form in some certain cases. So between now and that next test in the middle of November, like what the date is, but it's that week between Veterans Day and Thanksgiving, which there's a Monday off and a Thursday, Friday off on 2 weeks earlier and later in the month. We're going to work on, we started a little bit talking about optimization last class, what that means, and we're going to spend several more classes doing that, along with other things. It's a little bit too much to just do that all the time. But we're going to talk about some of the other things we've already talked about with rates of change, but now that we know how to find functions to represent them, not just talk about them abstractly, we can answer some slightly different questions than we could before. So we talked about, I believe, like pouring sand or something, but let's talk about pouring concrete. So suppose that I have the volume of concrete in cubic meters given by this V of x formula, where x represents the number of seconds since we started pouring the concrete. Suppose that I want to know a closed form function, meaning nice, finished, doesn't have to be simplified, but just something to represent the rate of change of the concrete being poured onto whatever it is, into a big vat of concrete, building a skyscraper or something. So the closed form rate function for this that measures this rate in cubic meters per second, if this original measures the amount that's been poured in cubic meters. So it's great to be able to know derivative rules quickly off the top of your head, because when you need to do something, rather than having to look stuff up all the time, if it's handy, mentally speaking, then you can just move on. Now, it's more important to be able to do something with it or know what it's for, because if you don't know what it's for, then you'd never know when to find a derivative. This v of x here, you can think of it in a few different ways, and if you're not taking a mastery test and concerned about should I simplify, should I not simplify, you can think of this a bunch of different ways. If you wanted to distribute this 30 to the two terms inside the parentheses, you could do that and look at it in a different format. You could even rewrite it involving roots if you wanted to. But just as it is, v of x, the volume of concrete poured after x seconds, is written as, we'll get a coefficient of 30 and then a simple subtraction problem. So this constant multiple of 30, we can just leave it alone, multiply it onto what the rate of change would be if it were just this 1 minus e to the negative x over 15. So, multiply on 30 to what would be the derivative of this. So what is the derivative of 1 minus e to the negative x over 15? Well, the 1 part, that goes away, it's a constant. So really all I have to think about is what's the derivative of negative e to the negative x over 15? And keep in mind that negative x over 15 is the same as negative 1/15 x. So you don't have to use quotient rule. Although if you did, you'd get the right answer, just maybe with more work. But the derivative of this 1 part is 0. The derivative of negative e to a power would be, I'm just going to write it off to the side here, negative e to that same power times the derivative of that power. Chain rule. So times a negative 1/15, which would make it a positive 1/15 e to the negative x over 15. Or, since this isn't a mastery test, I'm going to have to do something with this derivative. It might be nice to clean it up a little bit, as in just simplify those coefficients. 30 times 1/15 sounds like 2 e to the negative x over 15. You agree with that? Okay. So this is the rate of change of the amount of concrete that's been poured, or the concrete is, this would always be a positive valued function, since e to a power is always something positive, and then we multiply it by 2. So I could say that the amount of concrete is increasing, which makes sense since we're pouring it, at a rate given by 2 e to the negative x over 15. So this is the rate in cubic meters per second. This is the amount in cubic meters. Now this part B says that in 10 seconds past the start of the pour, some light signal turns on. I don't know, maybe they change the temperature, move some truck, whatever happens. So there's a light signal that comes on at 10 seconds in. And we want to write an open form function for a new amount, L of x, the volume of concrete that's just poured after the light comes on. So it says a closed form function, or open form function rather. Closed form is what we have before, the original given function. These closed forms are ones where it's just normal sorts of, oh, I plug in a 3 and I can evaluate, even if it maybe involves a calculator, like e to the negative 3/15 or something. But open form, you can think of that as involving sometimes infinitely many computations, or an expression that describes what has to be done, but it isn't really operations that we can do, such as integrals. And a lot of open form expressions that you've been asked to write thus far have been integrals. This one is too. An expression for the volume of concrete poured is related to this, but it's not the same as this. This is the total amount of concrete poured after x seconds have passed. And L of x is supposed to be an open form function for the volume of concrete poured after the light turns on. So x doesn't mean the same thing as it did before. It's at some point in time after the lights turn on, or this light turns on. And the light turns on at 10 seconds. So it's related to v of x, but kind of excludes what happened at the beginning, right? But what I know is the concrete's being poured at this rate, where x represents the number of seconds since the beginning of the pour times 0. But I want to know what happens from time 10 onward, or what does this cause to accumulate starting at 10 seconds in and going onward from there as far as I want. So thinking about exact accumulation, starting at time 10 and going on to wherever I want, this is the rate function, v prime of x, although I don't want to call it v, I don't want to use x's because I already have an x in place here. But I want to use this rate and let this spot, the variable values in that spot vary from 10 up through a general x. So I'm not going to use an x for it. I'm going to say it's, usually we use the t, but you can use whatever letter you want. Negative t over 15. And for each of these values of the rate, I use it for a small amount of time, dt. So this is my mdx sort of expression. So I let t vary from 10 through x, and this would give a measure of that accumulation from time 10 onward. So this is a way that we can write in an open form how much concrete was poured after time 10. So this is our L of x. It's a function of x because I'm accumulating from time 10 through time x. And the only other letter I see in here is t. The way that this notation works, I let t take on all the values from 10 through x. So t doesn't end up to be something that would end up in the end result. If it were a closed form function, t would disappear. But the closed form function should look something like this, right? Because I know that if this is what happens after time 10, I know what happened before time 10. I could figure that out. I could write it, I could say, oh, it's this expression. At any point in time, it would tell me, like, I could plug in 10. That would tell me what happened from time 0 through time 10, the total volume by time 10. Or if I wanted to know what accumulates, or how would I express accumulation during those first 10 seconds, I could write an integral from 0 to 10 instead of 10 through mystery x. But that's the niceness of this. Since we already know this amount function, the total amount of concrete poured, and this rate of change function, I can express anything I want about either one of them now, an accumulation from any given point to another in open form or in closed form, and a rate of change function, well, that's easy enough. We already wrote that. We could write it in open form with h's and stuff, but we know that it simplifies to this. But if I want to relate v of x, function that was given, and L of x, they're only a little bit different, right? V of x is accumulation since time 0, and L of x is accumulation since time 10. So since we're pouring concrete, I can be kind of specific about this. I can say that V of x is going to be more than L of x, right? More than by, well, the amount that was poured before time 10, right? Or up to time 10. So V of x, let me go back to this, sorry. There we go. Stubborn thing, sorry. All right, there we go. So V of x is larger. It's everything that happens after 10, what we just had, L of x, 2e to the negative t over 15 dt, plus what happened before 10. And I know what happened before 10. I can write it even succinctly. I don't have to write it in a open form. Say, oh, well, how much accumulated, or how much different are these? This is L of x, the stuff that happens after time 10. What happened up to time 10? V of 10, right? Which I could write like that, kind of a vague way to write it. Or since I have the formula for V, I could put in 10 for x. So that would be the same as 30 times 1 minus e to the negative 10/15, otherwise known as negative 2/3, plus L of x. V of x is more. How much more is it? Well, it's more by whatever was poured in the first 10 seconds. I know that it's more because I know that this V of x is an always increasing function. Its derivative is always positive because we're pouring concrete, just context-wise, like, oh, there's always going to be more after more time has passed, not less. But you can see this derivative is always positive. And this, if you think about its values, as x gets larger, I've got values here that are, well, they're approaching 30, essentially, because this part's getting larger, meaning this is getting closer and closer to 30. 30 times 1 minus something that's getting closer to 0, but it's positive. So in any case, then, the difference between V of x and L of x is the volume that was poured in the first 10 seconds, which is V of 10, otherwise known as 30 times that expression with 10 subbed in, which just happens to reduce. All right, so let's do something similar, but with our rocket ball question. So the rocket basketball and its velocity was measured by, or given by this equation, V of t equals t to the 1.3 power. Let's say that it was launched from a height of 6 meters above the ground. I think in one of the random homework questions, it gave you that as an extra piece of information. So this is the only function that we worked with in class. And when we were working with it originally, we were looking at that rate of change function and creating an approximate rate of change function by which we could create a approximate accumulation function and then think about what exact accumulation would look like. But how about if we think about what its exact accumulation looks like in a one-step process now, taking into account the fact that we know it started at time 0 at a height of 6 meters. So it wasn't launched from height 0, it was launched from height 6. Seconds, maybe think y final equals y initial plus mdx. And this is just asking for an open form function. But we are going to do a closed form one, or think about it for a little bit too. Add to the trickiness, this one wants a function where t is the output variable. So don't use t like we did in the last question. I want to write an expression for h of t, its height after t seconds have gone by, it's like my y final. What would I use as this in the spot of y initial here? 6. Yeah, so we start at 6 feet, and then we add to it. But it's not one constant rate of change for the rest of forever. It's a varying rate of change that we think of as having constant rates for extremely small moments. So I'm going to add up all of those infinitely many rates times time, and I'm going to actually use dx because I don't want to use t. I'm going to use t here. I'm going to let x vary from, well, the time that corresponds to height 6 times 0. At the beginning, 0 seconds after launch, my height was 6. And then after time 0, that height changed according to this rate, t to the 1.3 power, well, I'm going to call it x to the 1.3 power. Let x take on all the values from 0 through any mystery t that I want. So this is my rate, m. Each different value of x to the 1.3 power is used for a small moment of time, dx. And I add up all infinitely many of those. So this is the open form version of height. 6 plus whatever happens at the starting height of 6 plus whatever height I accumulate after that, after time 0, when my height was 6, due to that rate formulation. So here's a question. This h of t function, it's 6 plus something or another. That rate function, x to the 1.3 or t to the 1.3, can you think of what sort of this, I keep setting my hand down on this. There we go. Can you think of what sort of expression must be in h of t so that its rate of change, its derivative, comes out to be this v of t that we had, this t to the 1.3? What would need to be in there? We can work out some of the messy details in a moment, but what would need to have been in there in order for its rate of change, its derivative, to have ended up with a variable to the 1.3 power? Well, if I have a variable raised to a number power, that's the result of doing a derivative of a variable with a higher number power, right? Like if I had a t cubed in its derivative, there'd be a t squared. If I had t to the 17th power in its derivative, there'd be a t to the 16th power. So if in the derivative I have a t to the 1.3 power, in the original, the thing I took the derivative of, the accumulation function, there must be t to what power? 2.3. Now there's got to be some other stuff also, because if it was just t to the 2.3, it wouldn't work out to be simply 1 t to the 1.3. But think about what you would need. I can see from this that h of t needs to be something with a 6, because that's already there. 6 is closed form. That's perfectly fine. I can add on a 6. But this represents all the accumulation from 0 to t at this rate. I don't want to see the rate. I want to see what happens because of that rate, or I want to see the before the derivative. So something with a t to the 2.3 power, and maybe if you think of, oh, what if I took the derivative of this? Would it turn into that? Not quite, but at least the 6 would go away. So that's fine. But I need some sort of coefficient on this t to the 2.3 so that when I take the derivative of this, it ends up to be simply t to the 1.3. Can you think of what the coefficient would be in any form that we need? Yeah. 1 divided by 2.3. If I put this reciprocal here, if I were to use power rule now, the coefficient and that power, simplifying in the coefficient then, in the new coefficient, would reduce to a 1. 1 over 2.3 and 2.3. Now this isn't a very nice form. You don't like to have decimals inside of fractions, but it is equivalent, and you could call it 10 over 23, or multiply by 10 over 10. But this is a height function that has two properties. One, its rate of change is this, and two, at time 0, it has a height of 6. At time 0, you can see if you substitute in for t, I have 6 plus 0. Perfect. Or in other words, we've kind of played the game of what you did in Algebra 1 a lot in calculus version. Write an equation for the line that goes through 0, 6 and has a slope of 7. And you did that a long time ago, and that's a pretty easy question. This is the calculus version of that. Write an equation for a height that changes at this rate, t to the 1.3 power, and at time 0 has a value of 6, or in other words, in context, at time 0, the height value is 6 feet, what are we? Meters. So we're using an initial condition along with a rate of change to be able to recreate an entire function. This is actually what's called an initial value problem in calculus text, but generally it's the same thing as just using a piece of information aside from the rate to lock down one particular amount function or accumulation function. So, like I said, it's the equivalent of given a point and a slope, write a line. And it doesn't have to be a vertical intercept, although those are nice in algebra because the 6 shows up. It's nice in calculus too because the 6 shows up. All right, so one last question about this scenario, rocket basketball. Write an open form expression that gives the rocket's change in height from time 4 to time 5.6 seconds. And then think about how you could write that in function notation using, well, I won't tell you which function. We have a couple functions on here. So if I want to write an open form expression, so thinking integral, write some sort of integral expression that gives the rocket's change in height from time 4 to time 5.6. So, all right, integral from time 4 to time 5.6. Maybe think, all right, that's my interval of time. And so just remember when you're writing an integral expression, the integrand, the part inside the integral expression, is going to be something of the form mdx. So you want to use all of the different rates from 4 to 5.6 for a little bit of time. So you could use whatever letter you wanted at this point. It doesn't really matter. It's not going to end up being there at the end. So whether you use x or t, there's no conflict here because there's no t on that integral sign that has a second separate meaning. So I could write something like this, or I could use whatever letter I want. It's just a placeholder. It takes on all the values from 4 to 5.6. So this is an open form for that. But we just did write a function that tells me height. Here's an expression for height. So this is also the same as the change in height between time 4 and time 5.6. That's something that we could do given the proper function before we learned about derivatives or integrals or anything. I just want to know how much the height changed. So I want to know final minus initial. So that'd be h of 5.6 minus h of 4, if I use function notation. Now, since I actually have the function rule, I could even work that out. But what I wanted to point out about this is, if you do work out if you want to work out the value of this or write this out specifically instead of with function notation, if we were thinking about writing this out, I'd have h of 5.6 is 6 plus this lovely 1 over 2.3 times t to the 2.3 power. Ooh, 2.3. And then h of 4 is, oh, not t, sorry. 5.6. 5.6 to the 2.3 power. Minus, with a 4 in there, 6 plus 1 over 2.3 times 4 to the 2.3 power. And what I want to point out about this specifically, if you see all of this, in terms of simplifying, now there's a lot of stuff like, just throw that in a calculator. But notice there's a 6 in the beginning, and there's a 6 in the end after the subtraction. Those two would cancel out. So thinking of doing mental or manual simplification, it doesn't, the 6 doesn't really impact that. The change in the height has nothing to do with the 6. The 6 would help you determine individual heights. So that first expression with the 6 missing isn't the height at 5.6 anymore. It's how much the height changed between time 0 and 5.6. And the expression at the end, likewise, without the 6, isn't the height at time 4. It's how much it changed between time 0 and time 4. But if you want to know an amount or an accumulation at a single point in time, you have to have a starting point. It doesn't have to be a starting point. Some sort of initial tie-down point. It could be at time 1, time 7, time something. Kind of like if I told you, I've been driving to Tucson for 3 hours. Where am I? That's a weird question, but you can answer how far I've gone if I told you how fast I went. You can't answer anything unless I tell you where I started from or where I was at some point in time to kind of nail down where I've been going. You have to have some sort of initial information, I'll call it, although it doesn't have to be time 0, just some sort of input output pair to tie down the values of an accumulation function using the rate. You can go backwards or forwards in time from that using the rate. It's not at time 0 that you happen to have some information. But if you just want to know the change or the variation between 2 points in time, the initial values don't actually play a role. So if you hadn't figured that out or if you hadn't been given initial information, you can still compute the change and we can write an expression for it. Just this integral part on its own is just the change due to this rate between 4 and 5.6. Because initial values don't impact the amount of change, they only impact where you started from. All right, so moving on from that. Let's see. Let me click on things. There we go. So let's take a look at, well, this as long as it's up. Suppose this is a graph of a rate of change function f prime. So this is we've done this before in some directions and not in other directions, but suppose that this is a rate graph. In other words, I want to know on what intervals f of x, not the rate, the original accumulation, on what intervals f of x is increasing versus decreasing. And there's questions B and C here. On what intervals is f prime positive versus negative? And on what intervals is f prime increasing versus decreasing? So I can't, unfortunately, make this text smaller easily without making it invisible for everybody. So let's take a look at this graph. It's not moving or anything. But those are on the x-axis. Those are integer values, -4, -3, -2, -1. But think about when, based on this graph of f prime, On what intervals is f increasing or decreasing? On what intervals is f prime increasing or decreasing? And on what intervals is f prime positive or negative? So 3 questions, just the third one. Is f prime increasing, decreasing? Here, I'll take out some spaces. Maybe be able to see these all in the same. This is f prime. All right, so if this is a rate graph, I want to know when the accumulation is increasing versus decreasing, versus where is the derivative positive versus negative? Those are the same questions, right? Where is f of x increasing is the same as when is f prime positive. When is f of x decreasing is the same question as when is f prime negative, right? So the answers to A and B should be the same answers in order. Increasing equals positive, decreasing equals negative for those. So thinking about when is f of x increasing? When is f prime positive? Estimating. It's a little bit, this spot's a little hard to see. But let me see if I can scoot this a little, maybe. Please let me move this. From about, let me just call this -4, that spot there. It's a little bit to the left of -4. But to the left of -4, f prime is positive. This is a graph of f prime of x. So f prime has positive dependent values, positive rate values, all the way up through -4. So I'll call it -infinity through -4. And then not again until after 2, right? So from 2 onward, I've also got positive rate values, so therefore increasing accumulation. Now, decreasing is going to be the negative parts of this graph. F of x is decreasing when this rate graph is negative, so that's between -4 and -3. There's a few spots on here. Let's call this -4, -3, and +2. At those spots, that's when our rate is essentially 0, meaning we're not increasing or decreasing. So in terms of listing these intervals, I don't want to just skip over -3 and say, yeah, from -4 to -2, it's all decreasing. Not quite, because there's this kind of pause at -3. So I'll say -4 to -3. That interval, and then again on the other side of -3 through +2. So I've got f is increasing. I'll do this elsewhere. So f is increasing, and then pause, and then there's decreasing, and then a pause, and then decreasing again for a long time, and a pause, and then increasing afterward. So this is all talking about what f is doing. So if I were going to try to sketch f, I don't know any y values. Just kind of like the initial value situation from before. I don't know whether f has all negative values, all positive values, like is it really high, really low? All I know whether it's going uphill or downhill. But I know that it'd be going uphill, so I can sketch it down here, that's fine. It's going uphill from negative infinity onward, and then it's going downhill for a little bit, and then it goes downhill again for a long time, and then it increases. Now, it's probably not in straight lines, because it's not increasing at a constant rate. It's increasing at higher rates and then lower rates and so forth. But general shape-wise, to get an idea of what this would have to do, it would have to be somehow going uphill and then flattening out because it goes downhill. And then there's this flat spot, but then it goes downhill again. And just to use my graph that's already there, then it must turn around and go back uphill at this x equals 2. So I've got these spots where it changes from increasing to decreasing. In between spots, going from left to right, or as x increases, if the y values change from increasing to decreasing, the spot in the middle is called a maximum, or specifically, usually it's called a local max or a relative maximum. I don't know if it's higher than anything else, someplace completely different in the graph, but this is the highest spot around. We're at the top of a hill. Similarly, a spot like this, where a graph changes from decreasing to increasing, we would be at a local minimum or a relative minimum. Relative to the points around it, this has got to be the lowest one around because previously the graph was going downhill, the y values were decreasing, and then they changed to increasing. So in the middle, when it changes over, that must be a minimum. So this is, we talked about a little bit of this on Thursday last week. Now, this spot here, we didn't change. We just happened to pause for a little bit. We had negative derivative values, and then they went back to negative, which means although I was decreasing, I paused and then continued decreasing. This isn't a maximum or a minimum at that spot, but what it tends to be, unless it's a sudden weird spot in this graph, like a point in this graph, it's called an inflection point. And this one's a flat inflection. If you go back the same way you're going, if you've got a smooth graph, there's lots of more technical math terms for what makes something smooth versus continuous and like jagged or something like that. But if it's a smooth graph, no abrupt corners and things like that, if you have a negative, like this, we have a negative derivative that becomes 0 smoothly, then goes back to negative again. If you're hitting 0, and then if you're hitting 0 while having a negative derivative, and then you turn negative again, and there's no sudden jumps, it must be flattening out and then unflattening out. So what you reach is a minimum steepness in the middle there. So it's becoming flat, where beforehand the curvature is one direction, then afterward it's facing another direction. We talked a little bit about curvature, but this is curved up, whereas this is curved downward, and it switches right at that spot where that pause happens. Because what we've got is negative but becoming less negative, and then negative and becoming more negative. So I've got negative derivatives throughout here except for precisely at this negative 3 x value. But I've got negative values that are increasing, and then I've got negative values that are decreasing. So that's negative becoming less negative, or curving or turning upward graphically if I'm graphing the accumulation corresponding to that. And then still decreasing but turning downward when I've got this becoming more steep but negative, becoming more negative rate of change. So this, when you change from curved up to curved down, those boundary points are called inflections, and they don't always correspond to a place where the derivative is 0. It could be other spots as well, but just this one is. So, in any case, that was kind of the first two parts A and B altogether. Now part C was asking a different question. You're going to have, there's a bunch of IMath.AS questions that are about looking at graphs and describing intervals where the function you see is increasing or decreasing, and where other things related to it are increasing or decreasing or positive or negative. Make sure you read very carefully. So for instance, this first question of what this is a function look at what we've got a graph of. We've got a graph of f prime. I want to know where f is increasing or decreasing. Question C wants to know where f prime is increasing or decreasing. So looking at where f prime, this graph is increasing or decreasing, is looking at where is this thing that we already have a picture of going uphill or downhill. And that's not the same question as either of the previous two. A and B are really asking the same thing. F of x increasing is the same as f prime being positive. But neither of those are the same as f prime increasing or decreasing. So f prime increasing would be looking at this graph, when is this going uphill? And we haven't even talked about where are the uphill versus downhill boundaries on this, just the zeros of it. So here's a bottom of a hill here, a top of a hill there, a bottom of a hill there. Those are the boundaries between increasing and decreasing of the thing that we see. I can see from left to right that up and through, I don't know, maybe this is negative 3.75 or something. Negative infinity through negative 3.75. This function, f prime, is decreasing. And then it's also decreasing from negative 3 to, what is that, about 1/2? Negative 3 through 0.5. This graph is also decreasing. But the other two spots, other two intervals I should say, this interval and this one from here on out, this graph, the one that we're looking at, is increasing. It increases from this bottom of a hill to a top of a hill. So increases from negative 3.75 through 3. And then also again from 0.5 onward. So thinking about what we talked about at the end of Thursday last week about second derivatives, there is a fourth question we could ask that would be exactly the same as the third question here. Part D, on what intervals is f prime prime of x positive or negative? If I'm looking at a graph of f prime, where is its derivative positive or negative is the same as where is it increasing or decreasing. So if I were to put in additional questions here, let's see, D. On what intervals is f prime prime of x positive, positize, positive, negative. All right, and I'll scroll this back down. So where the second derivative of f, sorry, I didn't make it all italicized and nice. The second derivative of f, meaning the derivative of f prime, would be positive precisely where f prime is increasing. So these here are the intervals where f's derivative, the derivative of the thing we're looking at, is positive. Negative 3.75 through 3, and again from 0.5 through infinity. And on what intervals is the second derivative f prime prime? Not the second derivative of the thing we're looking at. The first derivative, the rate of change of the thing we're looking at. Where is that negative? No, it's where the thing we're looking at is decreasing. So any function and its derivative have that same relationship where a function is increasing, its derivative is positive, regardless of what you call the names of those, whether it's f and f prime or f prime and f double prime. They have that same relationship between accumulation and rate, or amount of the original, whatever the original might be called, and its rate of change. All right, so let's take a look more at that sort of thing. Let's see if I can clear this off. We were talking about first and second derivatives. So first, let's do some number crunchy sorts of things. If you have GC with you, you can do this on there or any other sort of calculator. But as a first step, at each given x value, 0, 0.5, 1, 1.5, and spread it out a little bit, 2 and 3, find the value of function g of x, the thing that's given, the value of its first derivative, which you would need to find first, but it should be pretty easy. It's a polynomial. And the value of its second derivative. Also need to find the formula for its second derivative. But again, pretty easy as it's a polynomial. So we're going to look at we're going to calculate out some of these, or if you want to split this up between you and the person next to you, you do one and you do one. Let's see if we can get these numbers. And we're going to look at the sequences of these numbers for the original, the derivative, and the second derivative, and see that they all go together. That it's not just magic that I said is true because. So if you're looking at the values of, and we're just looking at individual values. In reality, we don't have enough information to say that there's not crazy stuff going on in between, but this is just a fourth degree polynomial, so only a maximum of 3 turning points in it. It kind of goes up and down, possibly a while. If you're looking at the values of function g, the given one, at 0, let's do 0, 3, that one's an easy one. Substituting in 1 isn't too hard, should come out to be 2. And I believe subbing in 2 and 3 also give nice, whole numbers, but 1/2 and 1 1/2 do not. So it goes down a little, up a little, between 0 and 3. If you're looking at the values of g of x, if you're looking at the values of g prime, there's a negative in there and a couple of zeros. If you're looking at the value of g double prime, you should see, again, a couple of zeros and some positives and some, well, at least one negative. So let's think about what these sequences should do. Those should be your functions, by the way, for g prime and g double prime. These are rounded off to fit in here in large font, but it's 1.3125, it's just sixteenths, and 2.8125. The rest of these all come out as integers. But looking through g of x, I can see, well, between 0 and 0.5, g of x decreases, right? And if I look at g prime of x, okay, well, g prime of x at 0 was negative, so that makes sense that I should be decreasing for a small interval, 0 to 0.5, after that. But I can see that by the time I get to 0.5, that my derivative has changed from negative to 0. So thinking, oh, well, g must be decreasing, but then stops decreasing. Because then afterwards, it's increasing. And if I look at g of x, I can say, oh yeah, it was decreasing, and then it must have stopped decreasing someplace because it's increasing again. Now, just looking at this sequence of numbers, 3, 1.3, 2, that doesn't tell me that this is the lowest that I'm going to hit, but knowing that the first derivative is 0 there, changing from negative to positive does. So by combining what I see in the first, like just that first column, the first 3 numbers there, with what I see in the second column, I can see in the second column the derivative was negative, then 0, then positive. My y values were decreasing and then increasing. That one in the middle that corresponds to a derivative of 0, that must actually be a local minimum. It must be the bottom of a hill, not just something that happens to be lower, but it keeps going down for a little bit before it goes back up. That is the lowest number in that vicinity. So I can also see between 0 and 1, just looking at the first half of the chart number-wise, the second derivative was positive and then less positive and then 0. That second derivative being positive, remember, indicates that what it's the derivative of is increasing. So this being positive should tell me that the column before it was increasing. Well, it is. It went from -8 to 0 to 2. That's an increasing sequence of numbers. So that's good. But shape-wise, that also tells me that the original, this g of x over here, this is the second derivative of. When I've got positive second derivatives, since that tells me that my first derivative is increasing, that also tells me that the original would be curved upward or turned upward, whether it's going from negative to less negative to 0, or from slightly negative to 0 to slightly positive, or any part of that. That's an increasing sequence from left to right of derivative values indicates that my shape of my original, my accumulation, pre-derivative, would have been curved upward. And that also matches with what you know about polynomials. Like they kind of, curve up and down. They don't have any sharp points, but if I went from going downhill to 0 to uphill, that should be curved upward. So all of those concepts match together. You can go back and forth between them and see that, yeah, this all corresponds to things that we talked about, or the meaning of rates of change. So looking at the second half of this, the lower half of the chart, maybe starting with 1. So I can see that g of x continues increasing, 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 increasing. So beyond this 1.3, according to just looking at these values, it looks like g of x is just going uphill, uphill, uphill. But if I look at g prime of x, I can see a little bit more about how it's going uphill. So g prime of x, once we hit this minimum, I can see that, oh, it has positive derivative value. So that's going upward at a rate of 2 y's per x, but then going upward more slowly, and then kind of pausing before then by the time I get to 2, which we did skip over a whole unit here, by the time I get to 3, it's going upward very quickly. So looking at these, I can see it's going up, 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 but if we look at these details and say going up and then going up more slowly, pausing, and then going up rather quickly at the end. So thinking about shape-wise what this might mean, the first half of the graph, like, all right, so it's going downhill and then it changed to uphill between those numbers there. And then it's going uphill. And there's these numbers here to tell me something about what's going on. But this tells me a derivative changing from positive to 0 to positive is going uphill slowly, flattening out, and then going uphill again afterward. So also notice the second derivative is 0 at that same point. In order for that to happen, I was going uphill rather slowly. I have a minimum here at x equal to, let's see, 0.5. There's a flat spot where the derivative was positive, then changed to 0, then went back to positive again at x equals 2. So there must be a change in the curvature. There's this flat inflection at x equals 2. And the flat part of that has to do with the second derivative. We talked about second derivatives. Positive means curved up and negative means curved down. Well, 0 essentially means it's not curved. The second derivative of a straight line would be 0. The second derivative of lots of functions at individual points can come out to be 0, but it's this changing curvature or isn't curved. It can be either one. But this one I can see that I'm going from curved down to curved upward, and there's this inflection of this flat spot here at x equals 2. All right, so that's it for today. I will see you tomorrow night, if not before. Study well.